Okay, so remember, we only have three more lectures to complete the semester, and then we're going to have our third partial exam. Still, this week is a good time for you to go to the operators, ask questions if you don't understand part of the material that we are covering. Again, it's important for you to do well in this third exam if you are considering not taking the final. So the last thing we started discussing on Monday was confidence intervals. And one question that was asked by one of your classmates by the end of the lecture is that when you look at this value of alpha, or the probability of alpha in your table, in your normal table, if, for instance, you look at the value of 0.05, you'll see that you will get the negative value for the value of z. And that is, that's correct. But something that you need to keep in mind is that those signs for the z values are already considered here in this interval. So when you look at the upper bound, you already have the negative value for z in the lower bound and the positive value for z here. So if you look at this table, or this figure right here, you know that the probability of this n will be from 0, will go from 0 to 1, because it's going to cover all the area under the curve. So if you look at alpha of 0.05, for instance, it will be that this area. That area most likely is going to, well, it's going to be a negative value for z because it's to the left of 0. Okay? But in the same way, a value of z of 0.05 will be, let's say, negative 1.96. If you look at the value of 0.95, it will be the same value for z because this is a symmetric curve. So if this is 1, then if this is negative 1, this should be 1. Okay, because remember, it is symmetric with respect to 0. Okay, so I hope that clarified that question. The other thing that, please remember to collect your homework at the end of the lecture is they're going to be here in the table. So this is homework number 7. And the other thing is the sheet. Okay. You can keep it and bring it back at the end of the lecture. Okay. So I believe we covered this problem in class. The next thing is talking about how to use these confidence intervals to compute other things. So most of the time x bar, which is the sample mean, will not be exactly equal to mu, and the point estimate will be in error. The size of the error will be the absolute value of the difference between the population mean and the sample mean. We can be 100% times 1 minus alpha percent confident that this interval will not exceed this value. So by theorem 9.1, if x bar is used as an estimate of mu, or the population mean, we can be 100% times 1 minus alpha percent confident that the error will not exceed this number. And this looks familiar, right? This is part of the bounds of the confidence intervals. So what we are doing is just adding this value or subtracting that value in order to get the upper bound or the lower bound. Sometimes it's important to know how large a sample is necessary. So if you want to be within some specific confidence, you want to know how many observations you need to collect from the sample. to ensure that the error is estimated mu will be less than a specified value or amount E. E is the error. So if x bar is used as an estimate of mu, we can be 100% times 1 minus alpha percent confident that the error will not exceed a specified value or error E when the sample size equals this number. Okay, so we can estimate the sample size in order to be this percent confident that the true value of the population mean will be within the confidence interval. When solving for the sample size n, we round all fractional values up to the next whole number. So we're going to always round up. We can be sure that our degree of confidence never falls below this percentage. So let me show you an example here. So in this example number 3, we have the average zinc concentration recovered from a sample of measurement taken in 36 different locations in the river is found to be 2.6 grams per millimeter. Assume that the population standard deviation is 0.3 grams per millimeter. The question is how large a sample is required if we want to be 95% confident that our estimate of mu is off by less than 0.05. So in this problem we are looking for that value of n, or the sample size, that will give us that confidence for our estimator. So as we discussed, we're going to use this expression, n equals the z-value of alpha half times the standard deviation divided by the error, and that number squared. So we know the value of E, that's 0.05, and we are looking at 90% confidence interval. So that alpha half equals 0.05 divided by 2, which is 0.025. So remember, it's 1 minus alpha equals 95%. So that alpha is 0.05. So using these values, we can get the z-value from the table, and that will be equal to 1.96 times the standard deviation, which is 0.3, divided by 0.05, and this square, and that number is 138.3, which we need to round up, is 139. So n will be equal to 139 observations for the sample. And I believe the last question for the homework was asking something related to this. So that's the question that I asked you not to submit, because we haven't covered that portion of the homework. Any questions? Okay, so our continuation of this lecture is on the next group of slides. So again, in this lecture we covered the first 3 topics on this list. Now we're going to transition to the 4 or 5 topics on the next set of slides. So again, this is 1 and 2 sample estimation problems. This is part 2 of the lecture 13. And we're going to focus on the last 5 bullets, but we still need to define something else before we move to the next material. which is the single sample estimating the mean. The objectives for the lecture is still the same, but here's something new. There are many applications in which only one confidence bound is south. For example, if the measurement of the interest is tensile strength, the engineer receives better information from a lower bound only. This bound communicates the worst case scenario. So there will be some cases in which you are not interested on the upper bound. And this is one of those examples. You're just interested in that lower bound because that's going to measure the performance of the material that you're testing, for instance. So for those cases, it's better to apply a one-sided confidence interval. And these are developed in the same fashion as the two-side intervals. So essentially, what you're going to notice here in this definition for the one-sided, the upper bound will look like the upper bound of the confidence interval for both bounds. The only difference now is that instead of dividing that alpha value by 2, you're keeping alpha as an integer. Okay? So you're going to look only at the upper bound, but the alpha is going to keep, you don't have to divide alpha by 2 because you're only looking at one side of the confidence interval. Same thing for the lower side or lower bound of the confidence interval. So keep that in mind. Again, you are not dividing by 2 because you are only looking at one side of the interval. So for example, in a psychological testing experiment, 25 subjects are selected randomly, and their reaction time in seconds to a particular stimulus is measured. Past experience suggests that the variance in reaction times to this stimulus is 4 seconds squared. So this should be seconds squared. And the distribution of reaction time is approximately normal. The average time of the subjects is 6.2 seconds. So we have the average and we have the variance. That's the two pieces of information that we have. And the problem is asking, give an upper 95% bound for the mean reaction time. So the upper, as we discussed, the upper bound or 95% confidence is given by the following: x bar plus z of alpha times sigma over the square root of n. So again, alpha is an integer, and we know the values for x bar. This is 6.2 seconds. We know the values for the population variance is 4 seconds squared, and we know n. What is the value of n in this problem? 25. That's correct, because we have 25 subjects. So that's the sample size. So again, we're interested in 95%. So 95 equals 1 minus alpha. Alpha equals 0.05. So the value of z for 0.05 is 1.645. Again, this is coming from the standard normal table that I shared with you on one of the first lectures of this third part of the course. So we have all the information we need. The only thing that we need to do now is to plug in these parameters into the upper bound formula. So we have 6.2 plus the z value, 1.645, times the value of the standard deviation. What will be the standard deviation in this case? 2, and the square root of 25. And that is equal to 6.2 8:58 seconds. Okay, so what I will say about this material that we are covering right now is the important thing is that you make sure that you are paying attention to the details. So when you're looking at a two-side confidence interval, you know that you need to divide your alpha by 2 because you are looking at both sides. But if you're looking at only one side, that alpha value, you don't have to divide that value. Okay, now we're going to keep adding other cases in which you also need to be careful. So the next case is the case in which the value of the standard deviation or the population standard deviation is unknown. As you can see there in green in both letters, this is the case in which the standard deviation of the population is unknown. So far we've been assuming that that value was known. And as you can see here, that value is provided here, the variance. So you can compute the standard deviation based on the variance. So frequently we must attempt to estimate the mean and the population when the variance is unknown. So based on what we learned in lecture 12, we know that for such cases we can use the random variable t, and that is how do you compute that random variable? From a normal sample from a normal distribution has a t distribution with n-1 degrees of freedom. T can be used to construct a confidence interval on mu, or the population mean. In this case, the population standard deviation, or sigma, here is replaced by the standard deviation of the sample, which is denoted by S. And the standard normal distribution is replaced by the t distribution. So instead of using the standard normal table now, when this standard deviation of the population is unknown, we're going to use the t table to compute our confidence interval. So the confidence interval, indicated in blue here, confidence interval of mu and variance, or the population variance unknown, we can compute that confidence interval using this expression for the lower bound and the upper bound. So again, this is the case in which you don't know the sample, well, not the sample, the population mean and the population variance. You can compute that confidence interval using, instead of using the sigma or the population standard deviation, we are using the S value, which is the sample standard deviation, and we are using t instead of the standard normal distribution. And this is for n-1 degrees of freedom. On the same way, we can also compute a one-sided confidence interval under these circumstances. So again, we don't know the population standard deviation. So you see this expression looks familiar. The only difference is we still have alpha without having to divide that by 2 because this is one-sided. But instead of using z, we are using the t distribution. So let's look at this problem as an example and see if you can notice the difference. The contents of 7 similar containers of sulfuric acid are 9.8, 10.2, 10.4, 9.8, 10.0, 10.2, and 9.6 liters. Find a 95% confidence interval for the mean contents of all such containers, assuming an approximately normal distribution. Okay, so we know this is approximately normal, so the t distribution shares that shape for the normal. So what will be the first thing you will notice in this problem? Do you have the population mean? No, we just have the information of 7 containers. We don't have the population mean, we don't have the population standard deviation or the population variance. So those parameters need to be estimated. So using the data provided, you can compute the sample mean, which is x bar. And you know how to compute that? It's 9.8 plus 10.2 plus 10.4 plus 9.8 plus 10 plus 10.2 plus 9.6, everything divided by the number of observations, which are 1, 2, 3, 4, 5, 6, 7. And this x bar equals 10. So we found our sample mean. What else do we need to compute the confidence interval? The variance, correct. Well, we don't know the variance of the population, so we need to compute the variance of the sample. So the variance of the sample is computed using this expression. So the variance of the sample equals 1 over n minus 1 multiplied by the summation from I equals 1 to n xi minus x bar squared. So as I have mentioned in this class several times, some of you have problems computing that value. It's important for you to make sure that you understand how to compute the sample variance. So in this case, I have done this computation many times in class. In this time, I'm just going to provide you with the results. So make sure that you get to this value, 0.283. So we know now the value of the sample variance, and we know the value of the sample mean. So now we can compute our confidence interval. So again, this is for the case in which mu and sigma square are unknown. So for that case, we know that we can use this confidence interval. Okay? So we have x bar minus t alpha half times s divided by the square root of n less than mu less than x bar plus t alpha half s divided by the square root of n. So we have 95% confidence interval, right? So make sure that I can change this number anytime. Okay, so do not assume that you're going to use always 95%. Make sure that you follow the problem, what the problem is asking. So 95%, so that means that alpha will be equal to 0.05 and alpha half equals 0.025. So from table A4 of your textbook, and this table is also in the second package that I gave you with tables, T of 0.0025, sorry. T of 0.025 should be equal to 2.447. And here we are using how many degrees of freedom? N minus 1. So that is 10 minus 1, that's 9. Say that again? Oh, yes, right. Yes. I was counting 10. 1, 2, 3, 4, 5, 6, 7. Yes, this should be 6. Okay, so using this information, we can just plug in those numbers into the confidence interval. So we have 10 minus 2.447 times 0.283 divided by the square root of 7 less than mu less than 10 plus 2.447 times 283 divided by the square root of 7. And if you solve this, that mu is within 9.74 and 10.26. Yes, sir. Yeah, I guess what I gave you here is this is the standard deviation. Yeah. Let me check my notes. Yeah, that should be the standard deviation after the square root. Thank you. Make sure that you double check that number. Let's see. So this is the standard deviation. Thank you. Any other question? Okay, so another concept. Again, these are expressions and formulas that have been tested with real data, large data sets. And there's some approximations that work for this type of problem. This is the concept of the large sample confidence interval. So basically, when normality cannot be assumed and the standard deviation of the population is unknown, and third bullet over there, your sample size is greater than 30 or greater or equal to 30, we can replace the sample standard deviation, or we can replace the population standard deviation with the sample standard deviation, and we can have a confidence interval like this one. So again, under these conditions, we can go back and use the standard normal deviation of the standard normal distribution. But notice now that we are using the standard normal in combination with the sample standard deviation. Okay, so my recommendation for you is that you start preparing your formula sheet for the exam and also work on the homework problems, and you start listing the different cases and when and what type of confidence interval you can use for each case. So again, this is a different case. This is only in approximation, and the quality of the results becomes better as the sample size grows larger. So for example, yes, sir.
Let me prove this formula sheet will allow us to have an explanation next to each formula.
Well, you can have, for instance, for this confidence interval, you can list these three characteristics and say this is the confidence interval. And for example, here, you can say this is the case in which the standard deviation of the population is unknown, and mu is also unknown, so you use this confidence interval. Okay? That's a good question. So let's try to work on the problem with this confidence interval. So the SAT math scores of a random sample of 500 high school seniors in the state of Texas are collected, and the sample mean and the standard deviation is found to be 501, standard deviation 112. Find the 99% confidence interval, on the mean of the SAT math scores for seniors in the state of Texas. So what do we have? We have the sample mean, and we have the sample standard deviation. We know the sample size is high. It's 500 students. So N is 500. So since the sample size is large, again N equals 500, we can use the normal approximation. X bar plus minus z of alpha half times s divided by the square root of n. Okay, so this is one of those cases in which we are no longer using 95%, we are using 99%. So we need to find the value of alpha. So 99% equals 1 minus alpha. Alpha equals 1%, which is equal to 0.01. So alpha half equals 0.005. And the z value for 0.005 equals 2.575. So again, these values are coming from inside the standard normal table. So you need to go inside the table and find the value for z. So knowing those numbers, we can compute the confidence interval, 501 plus minus 2.575 times 112 divided by the square root of 500. Any questions? Okay, so this is very repetitive. You are basically performing the same steps every time you're solving a problem. The only thing that you need to be sure is that you're using the right confidence interval for the type of problem that you're studying. Let's talk a little bit about the standard error of a point estimate. So consider the estimator x bar. This is again the sample mean of mu, and let's say that the standard deviation is known. We indicated earlier that a measure of the quality of an unbiased estimator is its variance. Okay, so the quality of the unbiased estimator, if you want to select the best unbiased estimator, you know that you're going to select the one with the smaller values. So the variance of x bar, as we learned for the sampling distributions, equals the population variance divided by n. The standard deviation of x bar, or standard error of x bar, is the square root of this expression, which is the standard deviation. So the standard error of an estimator is the standard deviation for that particular distance. Okay? So for x bar, the computed confidence limit, which is here, can be written as, so this expression that you already know can be written as this. So you can change this value and call that number or this expression the standard error of the estimator, where the standard error or the standard deviation, or SE, is the standard error. Okay, so the only thing that we are doing here is just giving a name to this portion of the experiment. This is what we call the standard error of the estimator. Now, the width of the confidence interval, or mu, is dependent on the quality of the point estimator through its standard error. In the case where the standard deviation of the population is unknown and sampling is from a normal distribution, we can replace that population standard deviation with the sample standard deviation. And the estimated standard error can be computed using this. Thus, the confidence limits on mu are here. So again, this is the same confidence interval that you saw earlier. The only thing that we are doing is removing this expression and calling it the standard error of the estimator. Okay, so at the beginning of this course, I explained a little bit about some of the things that we can do with the material that you're learning in class. And I think one of the most useful things is the prediction interval. So basically what you will do is, using the information that you have from a sample, you're going to try to predict what will be the value of the next observation from your system or your experiment. So we're going to make predictions using prediction intervals. So sometimes the experimenter may also be interested in predicting the possible value of a future observation. So for example, in quality control, the experimenter may need to use the observed data to predict a new observation. So in quality control, what you do is you try to keep if you are producing a specific part or component for a computer, let's say, you want to keep, let's say, your component would not work if it is not able to fit within a particular slot. So you're going to be measuring those dimensions in order to determine if your component will meet the required dimensions. If that doesn't happen, then you have to check your process and see what is causing that difference. So in quality control, you're going to keep, let's say, like tolerance limits, so a lower bound and an upper bound, and you're going to be sampling from your process, and you're going to be measuring, and you're going to see if the sampling that you're making, the average, are within those tolerances. If for any chance that sampling of those elements that you're getting from your sample, when you compute the average, goes beyond or below or above those limits, then you need to check what is happening to your process. So this is used very frequently in manufacturing. You'll see those limits plot. You will see a plot of two limits, and you'll see how the process is changing or the variability of the process for a particular manufacturing line. So in quality control, we might need to predict the next observation, what will happen, in order to see if we need to go and perform a corrective maintenance to one of the machines, or if we can wait a little bit. So, for example, a process that produces a metal part may be evaluated on the basis of whether the part meets the specification of strength. So this is a different type of testing. Customer may be interested in purchasing a single part. The customer requires a statement recording the uncertainty of a single observation. This type of requirement is nicely fulfilled by a construction of a prediction interval. So to predict a new observation, we need to account for the variation due to estimating the mean and the variation of a future observation. So development of a prediction interval is best illustrated by beginning with a normal random variable x0 minus x bar, where x0 is the new observation and x bar comes from the sample. So we're going to subtract x0 minus x bar, and x0 is the value of the new observation. So since x0 and x bar are independent, both of them are random variables, we know that z, or the value of z, can be computed like this. We talk about the difference of means, and this is based on that discussion. So as a result, if you go through the process of derivation, this is what you're going to get. This confidence interval in terms of the new observation, which is x0. So the new observation, based on the sample that you're getting, or the samples that you're getting from your process, the new observation will have some limits. Lower bound and an upper bound. So let's illustrate this with an example. I do have an example. So this is the formal definition of what we just explained. And next we have the example. So due to the decrease in interest rates, the First Citizens Bank received a lot of mortgage applications. Recent sample of 50 mortgage loans resulted in an average loan amount of this amount and a population standard deviation of this amount. For the next customer who fills out a mortgage application, find a 95% prediction interval for the loan amount. So we are basing our next observation on the sample or the information that we have from the system, and we also have the population standard deviation. So using that information, we have x bar, which is 257,000. We have the value for our sample, which is 50. And we are looking for a 95% confidence interval, so the value of alpha is 0.05. So alpha half will be equal to 0.025. And the value of z for that alpha will be equal to 1.96. And we also have the value of sigma, which is 25,000. All that information is provided by the problem. Now we need to compute this prediction interval, which is given by this expression. 1 plus 1 over n less than x0 less than x bar plus z alpha half sigma square root of 1 plus 1 over n. Okay, so again, the confidence interval is for this next observation that is called x0. So we have 257,000 minus 1.96 times 25,000 times 1 plus 1 over 50 less than x0. And we also have x0 less than 257,300 plus 1.96 times 25k times the square root of 1 plus 1 over 50. So finally, we can state the final numbers. 207, 812.43, 306, 87.57. So what can you tell about those numbers? Yes. So this is kind of not giving you a lot of information. This is almost a 100K difference between the bounds. So in order to decrease those bounds, you can either get more information from the system, and you will make this value here very small. So the larger your observations, the larger this number is going to be. This number will be very small. And also the other thing that you need to find out is if you can decrease that standard deviation in order to make these bounds smaller. Okay. Any questions? So this is another case for the same confidence interval for future observation. Again, we have the case in which we know the population standard deviation, and we have the case in which we don't know that number. So this is the case in which the variance of the population is unknown. So as you can see, the main difference will be that instead of using the standard normal, we're going to use the t distribution. Process is the same. The only thing that you need to make sure is that now you're using the sample standard deviation, you're using the t distribution, and you also need to make sure that you're using the right degrees of freedom. You can also apply the same concept that we did for the confidence interval of the sample mean. We can have one-sided prediction intervals. The upper prediction bounds applied in cases where focus must be placed on future large observations. Concern over the small observations call for the use of lower prediction bounds. So again, notice that when you're looking at only one bound, the upper bound or the lower bound, you no longer divide by 2 in your alpha value. You use the alpha value as an integer. So here we have another example. This is just for one side. Meat inspectors has randomly selected 30 packs of 95% lean beef. The sample result in a mean of 96.2% with a sample standard deviation of 0.8%. Find a 99% confidence or prediction interval for the leanness of a new pack. So now we're going to predict the leanness of the next pack. So we know the value of the sample mean. What will be that number from this example? Yes, the 96.2, that's the mean of 96.2 with the sample standard deviation of 0.8%. Do we know how many observations do we have in this sample? N equals 30, that's correct. And do we know the population standard deviation? We don't. You only have the standard deviation of the sample. So for those cases, variance is unknown, mean is unknown, variance is unknown, then we use the t distribution. So we need to find this 99% confidence interval. So we can do x bar minus t alpha half times s times the square root of 1 plus 1 over n less than x0 less than x bar plus t alpha half times s times 1 plus 1 over n. What is the alpha value? So we know 1 minus alpha needs to be equal to what? Correct, 99%, because we're interested in a 99% confidence interval or prediction interval. So alpha will be equal to 0.01. And alpha half equals 0.005. So the t-value for 0.005 with 29 degrees of freedom equals 2.756. Okay, so again, this is coming from the t-distribution table. We have n equals 30, n minus 1 degrees of freedom equals 29. We have t-value for the confidence interval. We have the standard deviation of the sample, which we need. We have the size of the sample, and we have x bar. So we can compute this interval as follows. This is 96.2 minus 2.756 times 0.8 times 1 plus 1 over 30 less than x0 less than 96.2 plus 2.756 times 0.8 times 1 plus 1 over 30. X0 is less than 98.44 and greater than 93.96. So our next observation, we are not certain that it's going to be over the 95%, but these are the prediction limits for that next observation. Okay. We are almost there. We are almost done with the confidence intervals. I know this material is a little bit repetitive, but these are concepts that you need to understand specifically when you start doing experiments in your next courses. And now we have two samples. We started with the one sample confidence intervals. Now we are looking at two samples. And what we are interested in is in estimating the difference between two means. So assume that we have two populations with two different means, mu1 and mu2. So we are no longer using the information or sampling from the same population. So we can say, for instance, we are sampling from Texas State University, and we are also sampling from UT Austin. So these two different populations, you're going to have two different means, or two different population means, two different population variance. Okay, so a point estimator of the difference between mu1 and mu2 is given by the statistic x1 minus x2, or x bar 1 minus x bar 2. To obtain a point estimate of that population difference, we shall select two independent random samples and compute the difference of the sample mean. So we're going to select the sample from UT Austin, and we're going to select the sample from Texas State University, and we're going to compute the difference between the samples. So we can compute the confidence interval for that difference. And this is the case in which we know the values or the variance from both populations. So in this confidence interval, we are assuming that we know the variance of both populations. So for such cases, we can compute the difference or a confidence interval for the difference of the means of the population using this expression. And as you notice, if you assume that you know the values of the variance, once you assume that you know the values of the population variances, you will be using the standard normal distribution to compute the confidence intervals. So in other words, you're going to use the Z table. Okay, so here we have an example. So a study conducted in which two types of engines, A and B, were compared. Gas mileage in miles per gallon was measured. 50 experiments were conducted using engine type A, and 75 experiments were done with engine type B. The gas use and other conditions were held constant. The average gas mileage was 36 miles per gallon for engine A and 42 miles per gallon for engine B. Find a 96% confidence interval on the difference between the population means, meaning that the difference of the population or the experiments performed for engine B minus the experiments performed for engine A. So where mu A and mu B are population means of the gas mileage for engines A and B. Assume that the population standard deviation are 6 and 8 for both A and B, respectively. So from the problem, you know the population standard deviation. It's clearly stated that you have the population standard deviation, which means that you know that information, and once you know that information, you know that you're going to be using the confidence interval in which the standard normal distribution will be used, or the Z values are going to be used. Okay, so we can put the information for each engine in a table. So we have A and B, N equals 50, N equals 75, X bar equals 36 miles per gallon, and X bar for B equals 42 miles a gallon. Sigma for A, or the population standard deviation for A, is 6, it's right here. And the population standard deviation for B is 8. Now the confidence interval is 96%. So we need to compute alpha. 96% equals 1 minus alpha. So alpha equals 4%. Alpha divided by 2 equals 2%, which equals 0.02. So the Z value for 0.02 equals 2.05. Again, this is coming from the standard normal table. Any questions so far? So two important things. We have two different populations. We have data for each population, A and B. So you can use a table to differentiate the data for A and B, just like we did here. We know the population standard deviation for each population. And notice that it's not 99%, it's not 95% anymore. It's 96%. You need to find the value of alpha, the right value of alpha, and find the right value from the standard normal distribution. So what we have now is the following. We have to find the confidence interval for the difference of the population means. So we have x bar b minus x bar a plus minus z of alpha half times this expression, sigma square of b divided by n of b plus c max square of a divided by n of a. So in order to save some space, I'm putting both bounds on the same expression, so that's why I'm using plus minus. Okay, but you can have plus sign in one area and the negative sign on the other area. So this will be equal to 6 plus minus 2.05, the square root of 64 divided by 75 plus 36 divided by 50. So finally, you will have 3.43 less than mu b minus mu a less than 8.57. This is a 3. So what can you say about that confidence interval? First thing you can notice, if you expect to have a number close to the averages, make sure that you understand what you're doing here. We are not comparing for the confidence interval is not for the mean, for the population mean. Confidence interval is for the difference between the population mean. So what we're saying is the difference between the mean of the population A, population B, and population A will be between these numbers. So the highest difference will be around 8.57. Any questions? Okay, let me do one more thing, and then I think that's enough for today. One more thing. So the next thing is just basically the same type of problem, but in this case, we don't know the variance of the population. So what do you do when you don't know the variances? So far, what have been the strategy when you don't know the population variance? You use the t distribution, correct? And instead of using sigma, you use the sample standard deviation, which is denoted by x. So this is the same thing. We are looking at the difference of the population mean, but in this case we don't know the variances from the population. So what do? You find an estimation for the standard for the variance of the samples. Okay? And then you can use that estimator to compute the confidence interval for such a case. So this is the case in which you have the confidence interval. For the same case, but in this case, you know that you don't know the confidence, you don't know the values of the variances of the population, but you know that those variances are different. So that can happen if you have a sample very large from one population and a small sample from the other population. So these two things, again, in this case, variance is unknown, but the population variances you know that are equal. Variances are unknown, but you know that those variances are different. So next time we're going to start from here. So let me know if you have any questions. The other thing that the homework is here, and today I will not be in my office after 4 o'clock. So I'll be in my office from 3 to 4. If you cannot see me during those times, send me an email. Yes, thank you.